detail, the real conceptual core. On Thursday, I started this as well with them, and the way I did it with them is I really jammed them full of theory for an hour and didn't really contextualize it. And over the weekend, I realized it's probably not the best way to do it. I just wanted to get through it quickly so that then we could start the interesting stuff, applying it to something. But then I realized it's a lot of theory, there's not a lot of context, and it's probably easier to introduce a problem that we want to solve, right, to contextualize our theory, and then start building a theory to solve that problem, right? And in this class, this is just like regular first semester of CHEM, we have to come up with some toy model, right? And of course, our toy model in CHEM, or in thermodynamics, was a box of ideal gas molecules, right? These particles of no size or shape bouncing around randomly, no attractions, right? We need to have something like that to think about, to illustrate the concepts and the theory of this course. And we'll come up with lots of toy models. And it turns out all these toy models are very, very useful for chemistry. I don't want to spoil the chemical context just yet, but we should introduce a problem. And the problem that I want to solve is what's called the particle in a box. All right, and we're going to do something very simple. Well, you can already imagine, right? Remember ideal gas, we had particles in a box. Now we're just going to have one, right? One particle in a box. Same idea. So what I'm going to do is I'm going to build a box with infinite walls. Okay? A big trap. Okay? And I'm going to make the box a certain length. Right? And I'm going to, let's put it on a coordinate system just to make things easier. Let's let this distance be x. Right? This axis along the board be x. And the length of the box be L. Right? So this is at x equals L, and this is at x equals 0. Okay? So we have a box of length L. All right? With infinitely high walls. Right? So nothing can escape. All right, and what we're going to do is we're going to put a particle in. All right, and let's pick a particle. In fact, we'll just pick a class. We'll pick a natural particle that has, right, let me start over. In ideal gas, we pick the particle that has no shape, no size. So let's pick one with no shape. It has a mass, but it has no shape. Let's pick an electron. So let's put an electron in here. All right, remember that an electron is a point mass, so it has no shape. It's just a point, but it does have a mass and a charge. Call that the charge, of course, is -1. The spin, we'll come back to that. What won't be relevant here, but we'll need it later, is 1/2. And the mass of an electron, I'll write it down in kilograms. This is a good number to write down, or just remember to look up. We'll call the mass of the electron ip sub e. It's in the mass of the electron. And it's roughly, I won't write all the digits, but it's roughly 9.109 times 10 to the minus 31 kilograms. Okay. All right. So we know the mass of our object, we know it has no size, and we know the dimensions of the place that we put it. Okay, so now the question, let's imagine now we're in physics, right? We're in Dr. Popolowski's physics class, and we want to figure out, well, what is this electron doing in this box, right? So what do we do in classical physics to solve for this system? Classical physics says we solve Newton's equations to calculate the position of the atom, or the electron, at any point in time. Right, we want to solve the equations to get the position as a function of time, right? So in classical physics, we're going to solve for the trajectory, right? X of t. Right, classical physics. Right, we use Newton's equations, F equals ma, all that junk. get an equation for motion and solve for it for the electron. Okay? You might also want to know the momentum, the velocity of the electron as well. Right? So often we'll look for the derivative of position with respect to time, which is the velocity as well, which I'll call v of t. Right? The velocity and the position. Right? And if we know how fast it's moving and where it's at, we can calculate its position at any point in time. Right? That's all we need to know about this electron to know exactly what it does in the box by itself for classical physics. All right, but the problem is in quantum mechanics, an electron is not just a particle, but it functions like a wave. We talked about the double slit experiment. Right? It shows that an electron is a particle and a wave. Newton's physics don't account for that, the fact that it's a wave. Right? It only treats it like a particle. And in fact, when you try to solve the equations of motion for this electron in the box using Newton's laws, you get the wrong answer. Right? And that's because we make this assumption that it's a normal particle. We know exactly where it is at all times. But that's obviously not the way electrons work, right? That's the whole point of this entire class, is because that fails. Right? So we can't use this solution. The strategy is the same. We set up a problem, we put a mass inside of the box, we want to figure out how do we represent the position or the behavior of that electron with a function. Right? So the strategy in QM is the same. We need to find a function. Let's just call it f of x comma t, right, to position in time, that encodes the behavior of the electron. Right? And that means that it has to be, and what do we mean by the behavior? Well, that means that we have to consider the fact that it's going to propagate simultaneously like a particle and a wave. Right? That means that this approach using Newton's mechanics won't work, right, as I've said before. We need a new approach to calculate the function. Right? Same idea as before. Newton physics, we're still calculating position f of x of t that tells us the position and time of the at a given time of the particle at all points. So the question is how do we do that? And that's not there's no obvious answer to that. In fact, historically, what they did is they just guessed. Right? They had this idea that that a particle, like an electron in a box, works like a wave. Right? So maybe they should use the physics of waves to solve for it. Now, I'm not going to talk about the physics of waves, but instead I'll just come with the results. And so when you do, a famous physicist named Erwin Schrödinger had this exact approach. He said, well, I have an electron in a box or an electron orbiting a proton, right, in a hydrogen atom. It acts like a wave, so let's use wave mechanics to understand it. So Erwin Schrödinger, we call this the Schrödinger approach. He comes up with a guess for the physics. I mean, he literally does. He just guesses it. He has no idea how it's going to work, but he has some insight about how it functions, so let's come up with an idea and see if it works. He literally guesses, and he got it right. All right, and his guesses have, and his approach that we call Schrödinger approach, which uses integrals in calculus, has a set of rules that all systems, quantum mechanical systems like this particle in a box, have to satisfy. All right, so there's a set of laws, right? Newton's laws tell us how normal particles work, and these laws of quantum mechanics also tell us how small particles that act like waves also work. All right, so it's an entire new set of laws, if you will, that solves it, that includes this wave-like property. We don't often call them laws, though, but rather we call them the postulates of quantum mechanics. The reason why they're not called laws is because it turns out there's different ways to interpret the laws. There are different ways to interpret the behavior of a particle that's both a particle and a wave. And you just have to make a decision about which way you interpret it. And so we don't call it laws because there's different ways to state them. Instead we call them postulates. They're statements we assume to be true. Okay, so they're not laws. I mean, that's all a law is a statement we assume to be true, but it's a slightly weaker than a law. Okay, and in fact, all the great scientists of the 1920s came together at a big conference in Copenhagen and came up with this set of rules, these postulates. It's not the only way to define things, but it's the way that we'll define things, and it's the way that typically that the rest of the world defines things. And this is called or historically called the Copenhagen interpretation. There's different ways to define the rules, but this is the way we do it. It's kind of the mainstream way to do things. We'll find that there are things in the Copenhagen interpretation, these postulates, that don't make any sense. They're just completely absurd. And of course, back in the day, they had a big problem with these absurdities. We've already talked about some of them. We don't get rid of those absurdities. We just accept them to be true and work around them. A lot of people weren't happy about that, so they came up with other interpretations of these postulates that solve some of the issues. But it turns out that they also make crazy assumptions as well. So it's equally absurd in its own way. But there are certain things about this interpretation that people don't like. But we're going to assume it to be true. And it's actually the easiest way to think about things, in my opinion. So there's about 6 of them, right? And we won't go through all of them today. We'll only go through about 2 today, 2 or 3. And what we'll do is we'll tackle this problem of a particle in a box with the tools as we learn them. We'll learn the postulates, get to a certain point, and be like, well, we need to figure out what to do next, and then we'll bring in some more rules and more tools. Okay? So we'll kind of build this problem up from the ground up slowly. Right? And so I want to introduce the first one, the most important postulate. Postulate 1, the wave function. All right, here we define what we're looking for. Right? Classical physics for the electron, we're looking for a trajectory. Position as a function of time, or the velocity as a function of time. Right? And here I said we have to look for a function that's dependent on the position and time that encodes the information about our system. And that's the wave function. We call it the wave function. Okay, so a state of any quantum mechanical system, like an electron, is completely specified. And I mean completely, by its wave function. Okay. We typically write wave functions with a specific symbol. The Greek letter psi looks like a pitchfork. And it's a function of position and time, just like we want. Okay? The goal is that we want to find this wave function for our problem. Right? We don't know what it is. We don't know how to figure out how to calculate it yet, but we know we want to find it. That's what the postulates imply. And this wave function has a couple of very specific properties. It has one really important, very important property. So not any function can be a wave function. Okay, so let's go back to our box for a second let me try to explain this property before I introduce it. So let me just draw my box real quick and have to follow. And let's imagine we don't know where the electron is in the box. We put the electron in, and it's just somewhere. Right? We don't know where. But let's say it's between x and x plus dx. Okay, so let's ask the question. Actually, let me ask this: what is the probability of finding the particle, or finding the electron, between x and x plus dx. Okay, we're going to make an observation, right? And we look between in that small region, and we ask the question, what's the probability of finding the particle there? All right. The definition of that, so we'll call it the probability of finding the particle between x and x plus dx, turns out to be equal to the absolute value squared of the wave function times dx. All right, so the probability is determined by the square of the wave function. Okay, so what that means is that the probability of finding the particle between 2 points x and y is going to be the integral from x to y of psi squared dx. Okay. Now, this is different than thermodynamics. Now, remember, this is a long time ago, but we talked about the ideal gas. We asked the question, what's the probability of finding a particle in a certain range of energies? And we had this function e to the minus e over kt. That was the probability. Right? Wave functions have this restriction instead, that their probability has to be determined by the square of the function. Right? It might not be clear why it's the square yet, but it will become obvious as we go through the math. Okay? The square is the important part. In fact, the square of the wave function is the most important part of the wave function. So let me write that here. The probability of finding the system in a certain position, state, is proportional to psi squared dx. Okay. What we'll find is, in fact, for instance, we'll talk about, once we get to molecules, we'll want to come up with a wave function for our molecule. Molecule is a quantum mechanical object. It's a particle in a wave. We want to use this postulate. We want to find a wave function for a molecule. That wave function completely specifies everything we need to know about the molecule. Its structure, its energy, anything you can think of we get from the wave function. Right? All of its information is contained in this function. And imagine now you want to image that molecule. Right? You're going to take a picture of it. And I'll show some pictures of some molecules. And what you're observing is not the wave function, but the wave function squared. You're asking the question, what's the probability, where is the highest probability of finding an electron in my molecule? Well, that's just asking the question, what's the structure of my molecule? Where are the nuclei and where are the electrons? And the question you ask that molecule is, show me your psi squared, right? That's your probability of finding those electrons. So if in regions where there's a high probability of finding electrons, which are bonds, you're going to have a bright line, right, for your bonds. And outside of the bonds, there's not very much probability to find the electrons, and so it's dark. Right? So a structure of a molecule is just psi squared. Right? Psi squared determines the observed structure of your molecule. Right? You're measuring the square of psi. Right? The reason why it's squared is very important, but we haven't quite gotten there yet. So just hold on to it. But remember that everything that we're going to see this time and time again, everything that we want to learn about the molecule, like physically, when we go do an experiment, we're going to ask psi squared questions. The more importantly is this. Maybe we'll see where to write it. Let's write it here. Is that when you integrate the probability across all space. All right, so let's just go from minus infinity to infinity of psi squared dx. All right, what's the probability of finding our particle in any part of space? Well, the probability has to be 1. Okay, so not only is the probability proportional to psi squared, but the integral over all space of psi squared dx has to be equal to 1. It's normalized, as we call it. It's just called normalized. Right, that should make a lot of sense, right? All I'm asking is, what's the probability of finding the particle anywhere? Well, that's 100% chance, or 1 probability, right? So the whole thing has to integrate to 1. Okay, so even though this doesn't tell us a lot right now about what a wave function looks like, what it tells you is that not every function can be a wave function. Because imagine if you think psi, the wave function that specifies a molecule is x squared. Function x squared. When you square that, you get x to the 4th, and when you integrate over it, you get infinity. It doesn't converge. Then x squared can't be a wave function, right? So only certain functions satisfy this property, and those are the only ones that can be wave functions, right? So it already limits the kind of properties and the kinds of things that actually are real objects, real quantum mechanical objects. And it has to be limited to these. Okay, so what we're going to do with our particle in a box is figure out a way to find this wave function, which tells us everything about the electron in the box, such that that wave function satisfies this property. Right? It also satisfies some other properties. Right? We're going to continue to limit the kinds of things that a wave function can exhibit. Very specific. Right? Again, we can't really do much with this map at the moment. So now the question is how do we find this? Okay? But in order to figure out how to find a wave function for our system, the solution to our system, if you will, is we have to figure out, well, what can this thing do? Right, what can it tell us? Right, what are its properties? And that leads us to postulate 2. Which is that it's the postulate of what are called linear operators. And I'll explain what a linear operator is. Properties of a quantum mechanical system, which of course is represented by a wave function. Okay, so we have a function psi, defines a quantum mechanical system. The properties of that, the way we ask questions, what's your energy, what's your position, are given by the results of a so-called linear operation on the wave function. All right, now that does not mean anything at the moment, but let's ask what a linear operator is. All right. You work with linear operators in math every day. Okay, let me give you some examples of some linear operators, and I'll explain what linear means in a second too, once I explain what operators are. Here's a good operator, one that you literally use every day. Define the plus operator. It's a function plus that takes in 2 variables x and y, such that plus x and y equals the sum of x plus y. Okay? So for example, if we take the plus operator and add to it 2 and 1, we get 3. That's a linear operator. Addition is an operator. Right? What an operator is a function that maps one set of numbers to another. They're slightly more restricted than just a function. They have other characteristics, but just bear with me. Right? Plus is an operator. Here's another example. Define the star operator of x and y such that x times y right? You get the product. Star of 2, 2 is 4. Right? That's an operator. Right? It's an operation, you take two numbers, you put it into a box, and it spits out a new number. Right? So those are operators. Here's another one. You can have operators that take functions in and bring out numbers, or other functions. Here's another example of an operator. The derivative. Take the derivative of x squared, what do I get? 2x. Right? We're taking a function, operating on it, and getting a new function out. Right? We've seen operators all the time. Right? So each property of our wave function, position, energy, momentum, whatever you can think of, anything you'd want to ask the particle about, has an operator associated with it. But not only that, it's what's called a linear operator. And let me explain what a linear operator is. Let me make sure I have the notation proper. If it satisfies linearity, which is a circular comment, but imagine an operator f that takes in numbers x and y. A linear operator is one where this becomes you take the operation on a sum of numbers, you get the sum of the operators. Okay, do them individually. Okay, so for instance, here's some notation, because we'll use this notation a lot. We write operators. We mark operators in QM with a hat. So the operation for distance or position is x hat. We put a little hat on top. Or energy, E, is E hat. Right? So anytime you see this little hat on top, that means it's an operator. Okay? What is an and we have very, very specific operators in this class. Right? What kind of operators are appropriate for quantum mechanics? What are, let me ask in a different way. All physical things that you can measure about the system has an operator associated with it which satisfies certain rules. One, that it's linear, right? That when you take an operator on, say, two wave functions, you get the sum of the operators evaluated on one wave function. Every operator we're going to do satisfies this. There are operators that don't satisfy this. It might be an interesting question to think about what operators, what kind of math kind of operations you can do that don't satisfy this. And it's actually quite simple to come up with one if you think about it a little bit. This doesn't work. I should leave that up, I'm sorry. Okay, and so we need one more property to tell us what kind of operators we want. So this is postulate 3. And there's different ways to write this. We'll call it the eigenvalue eigenvalue criterion. All physically measurable quantities all right, so that's position, energy, momentum. What else can you measure? Spin, et cetera, et cetera. Anything that you can measure in the lab for your molecule, structure, position, corresponds a linear operator that also satisfies the following property. So let A be a linear operator, and if a wave function x satisfies the requirements of the system, right? It represents a system, a real system. Then when you apply the operator to the wave function, all right, I'm going to take the operator, I'm going to do something to this wave function. You get a number back times the wave function. So this is a real number, and this is the wave function unchanged. Let me explain this qualitatively. Imagine we have a box. Our operator box. It's a black box. And its input is some quantum mechanical system or electron. It doesn't matter. A molecule. Right? A is going to ask it a question. Right? And if this is a valid, if it's a valid wave function for a real quantum mechanical system, like it satisfies our particle in the box, then what it spits out every single time is a real number, A. This is what we call the eigenvalue. It's a real number. For instance, if we were to ask if A were the position, if the operator A is position, then the number that comes out is the position of the atom or the particle. Call that the eigenvalue. And the wave function comes back out unchanged. Okay, so what this says is that in order to measure something of a wave function, ask it a question, you can only ask it things that return a real number and leave the wave function unchanged. We're going to come across measurements that manipulate the state of a system. There are certain measurements that you can make to a quantum mechanical system that change the state of the system. That's a real problem for us, because when we want to ask a question, say, what energy are you at, electron? We don't want to change the electron's energy. We don't want to change its position, because then we're not going to have a realistic result, because we're manipulating it by asking it a question. All right, so we have to ensure that the questions we ask it don't manipulate the wave function. All right, so any sort of real observable energy, position, momentum, things that we want to ask the particle and get an answer that's unbiased, then that means that those observables, momentum, position, energy, have to have an operator that satisfies this property. Okay, that when you apply the function to the wave function, you get a number back times the wave function. That guarantees that this is a real number, that's a real observable, something you can actually measure. If we go through this math and find that this is not true for some operator, then it's not going to give us a real physical observable we can measure. The only things that we can measure physically are things from operators that do this, that give back the number times the wave function. It's kind of hard to see the structure of this. Once we start talking about operators, the wave functions a little more, this idea of eigenvalues will become more obvious, that there's some internal mathematical structure and logic that determines all of these rules. But we're not quite there yet to deal with it. So let's just hold on to it. So there's a lot of things here that seem odd, but as we apply them and as we start to evaluate the structure of these things, they'll become more obvious and more apparent. But this should be a reasonable thing to assume. Right? If you're going to ask a system a question, you better hope it doesn't affect the answer, right? That your question doesn't bias the answer. And that would be shown by taking the wave function, which is your system, asking a question and getting a new function out, right? Changing the state of the system. We don't want that. Right? We want the same thing to come out as it comes in. Okay? So now, here's an interesting thing. We're already at the point where we can start thinking about how to solve this problem. We're not even halfway through the postulates, and we already have an idea. So let me write this. So we know. So let's come back to our electron again. Now we want to ask the question, what's its wave function? right? That's what we want to solve for, right? That's what postulate 1 says. In order to figure out how this electron moves in this box, we need to find its wave function. How do we find the wave function? Well, we have an algebraic equation we can solve. We know for some operator A, that when we apply A to wave, we get a number back times the wave. Now let me subtract both sides from A psi x. What that means is that this is equal to 0, right? This is an algebraic equation. We can solve for psi of x. If we know A hat, we know what that looks like. We know A, we know what comes out of that box. Then we can solve for psi. Right? That's all that's left. Right? So now we just have to come up with the right operator to choose. Right? What question do we want to ask that will tell us the most information about the system? And we'll use the same quantity, the same measurable quantity that we've used the entire year, energy. We're going to ask the question, what's your energy? And come up with this eigenvalue equation, this operator equation for energy. And then solve for psi of x. Right? We're going to get an algebraic equation. In fact, it'll be a differential equation. And we'll be able to solve for the function that satisfies that differential equation. So let's do that. We don't know what the operator for energy looks like, but we can come up with one. Let's do that. Okay, so let's do that. So what we want to do is find, we'll call it E hat, the energy operator. Okay. And then we'll apply it to that equation there and solve for psi. Okay, so let's think about energy for a second. How do we break energy apart? Well, there's a really easy way to do energy. Is write the total energy. Right, we just have a particle, so let's just use a basic understanding of particles. The total energy of the particle is the kinetic energy plus the potential. Right. So what we can say is that the total energy operator is the kinetic energy, which I write T, plus the potential energy V. Right? They're linear operators. So if the number is the sum of the two, then the operator is the sum of the two operators. Thankfully due to linearity. So this is kinetic. We'll always write kinetic as T, and potential as V. All right, so now we have to ask the question, what's the kinetic energy and the potential energy of our electron? So let's start with kinetic energy. Well, I know kinetic energy is 1/2 mv squared. We're going to have to make the velocity we'll have to make the velocity an operator. Mass is not an operator, it's just a number, right? It's the mass of the electron. And now let's ask the question, what's the potential energy of this system? And in fact, it's really easy to determine. Potential energy is how much energy is stored in the box itself, preventing the atom. Does it have an attraction to the atom or not? Right? How does the electron feel when it's in the box? So how much potential energy does it have inside the box? Well, none. Right? It can freely move between the ends of the box as much as it wants. So the potential is 0 if the position of the electron is between 0 and L. Oh, sorry, X. All right, I'll write that down over here. So if the electron's in the box, it feels nothing by the box. It's free to move. Okay. Now what about outside the box? Well, the box has infinite walls. So in order to get over those walls, it needs to have infinite energy. So outside of the box, the potential energy is infinite. So if x is less than 0, x is greater than L. Okay? Really easy, right? So the potential energy is 0 when it's in the box, and it's infinite when it's not. All right? That's really easy. That's an easy operator, 0. And we don't even have to consider the infinity part, because we know there's no probability of finding a particle of infinite energy. So we can just ignore this part, right? We just have a 0 there. So inside the box, all the energy is kinetic. The problem is, and we'll learn why, velocity is not a good thing to measure about a wave. It's not very easy to define velocity. Okay, so we got to rewrite velocity. We got to write kinetic energy a different way. And the way we're going to rewrite it is just by using a little bit of unit analysis, but I won't go through it, but just bear with me, is that the kinetic energy can be written as the square of the momentum divided by 2 times the mass of the electron. Okay. So what does that mean? So the total energy inside the box is going to be p squared over 2me inside. Right? There's no potential energy, it's all kinetic, and infinite elsewhere. Okay? So we don't ever have to consider this, right? We only have to look inside the box. The outside of the box is meaningless. The particle will never be found outside the box because the energy is infinite. So now what we have to do is write momentum as an operator, right? What does p squared look like? What's the function that satisfies all of these postulates for momentum? And it turns out that the formalism for momentum is very weird. It doesn't look, in classical mechanics, so in classical physics, you have an electron moving. So here's my electron. It's moving around. Classically, momentum is the mass times the velocity of the particle. Okay, so m sub e is moving at some velocity. Okay? Well, we could write that, but again, we have a problem now, is we have velocity, and I just said velocity is not something you can really determine easily for a wave. So let's not use that. So it turns out that quantum mechanically, you can derive this, that momentum is a weird number. It's I over Planck's constant divided by 2 pi minus I, h over 2 pi, times the derivative with respect to x, the position. Right, so if you think about it, this is kind of like velocity. Well, no, it's not actually. It's a position derivative, not a time derivative. I take that back, right? This is distance. Remember, this is change in distance with respect to time. This is change in distance, or in position. There's no time in this at all. It's very strange. This is a really important thing to write down, I think. We'll use this a lot. And eventually, once we get to it, I'll explain why it has this form. Okay, we don't have a good reason for that yet. But there's a good reason why it looks like this. I want to add one more piece of notation for you. And I'm going to write it over here. Let me just remind you of this constant. Just recall, and again, this is our gas constant for quantum mechanics, if you will, the number that we use for every calculation. Remember Planck's constant, which is h 6.626. It's approximately 6.626 times 10 to the minus 34 joule seconds. All right, I'm going to define another constant called h bar. I'll never call it anything other than h bar. And it's just an h with a cross through it. And this is a number that's used all the time in quantum mechanics. It's Planck's constant divided by 2 pi. And the reason why it's 2 pi is due to the fact that we're dealing with waves. So you have to divide by 2 pi radians. So it has something to do with the frequency of the light, the angular frequency of the light. So that's why there's a 2 pi in here for a factor of a circle. Right? A circle has 2 pi radians, so you cancel that out. And so you take this number and divide it by 2 pi. I don't know what that number is off the top of my head. I'll look it up real quick. I actually have never memorized h bar. I just divide it by 2 pi. So I will, from now on, I will never, okay, it's 1.05. I will almost never call it reduced Planck's constant or Planck's constant divided by 2 pi. I'll call it h bar. I'll write that here. All right, that's what everyone calls it. Okay, 1.05. So when it's kind of the energy scale of a wave, right? This 2 pi. It's like per radian, if you will. Right? How much energy there is per radian per second. Okay, so we use 2 pi a lot in this class because of a wave. There's 2 pi radians. There's always phase in a wave and oscillation, so we always account for that. And that's where this 2 pi comes from. So we can rewrite this, and you'll see this in your book, this version all the time, minus I h bar d by dx. Okay, so to calculate, so let's just think for a second. What if we want to calculate the momentum of a particle? So here's our particle in a box. We're going to take its wave function. We don't know what it is yet, but we know that when we apply this, we're going to get a number back, which is the momentum in the x direction times the wave function, right? That's the rule. We don't know what the wave function is yet, but we know it's going to give us a number, right? This is the momentum. And what do we do on the left-hand side? Well, what we do is we take the derivative of the wave function with respect to x and multiply it by minus I h bar. I is the imaginary number. And we get a number out. So this is the same as writing minus I h bar d by dx psi of x. I'll write it at the top. D psi dx equals some number piece of x times psi. Now here's something interesting. And this is unique to quantum mechanics. And we'll try to understand this more as we go through the class. What did I say about this number? This number right here must be real, right? We're going to get a real number out, right? The particle has a momentum. We can measure it. We only measure real numbers, right? We don't measure imaginary numbers. It's real. So this is real. But look on the other side. We have an imaginary number here, right? Minus I. So what does that say about, so we apply a minus I to our wave function, and then we get a real number back. What does that must mean about the wave function? Well, the wave function is complex. The physics of our system aren't necessarily real. The wave function might be a complex value function. It might be complex. It might have i's in it. Right? So now what we have is a function that represents a real system, something we can touch and feel and measure, but the function that's associated with it, this wave function that completely specifies the system, is complex. That's very odd. That's a very unique part of quantum mechanics. In classical physics, your functions, your trajectories are real, everything you measure is real. But in quantum mechanics, you're necessarily complex. Not always. We can choose situations where we're always dealing with real numbers, and that's what we'll do. But notice that there are situations where your wave function has to be complex in order to get a real number out for a measurable, like position or momentum. And there's a really interesting way to look at this. This is a little bit of a digression, but I think it will help clarify why a wave function might be complex. I'm just going to do it graphically. And then we'll come back to our problem. How much time do we got left? A little bit. Okay, cool. So remember, so our electron's wave function might be complex. But the electron is a wave. So in time, it oscillates from a phase of 0 to a phase of 2 pi. I'll draw this. So for instance, let's imagine that our wave function is a sine wave. All right, so let's call this psi of x at t equals 0. All right, so here's our electron's wave at t equals 0. What happens at t equals some other time? Well, imagine that the system is moving in the x direction. Electrons moving through the box along the length of the box. After a while, the wave will propagate, right? So after a little bit, it'll look like this. Right, so this might be y x t equals 1, for instance, or something. Whatever, it doesn't matter. And then after a little while, it'll propagate like this. And you can keep going, right? We can just keep going, right? And eventually what happens is, let me find one more color to draw it properly. We'll do it in pink. You're going to come back to a situation where your wave is now back at its original position in terms of its phase. That's overlapping with the original t equals 0, right? You're going to get the same wave back eventually, right? Because this wave is moving like this, and eventually it's going to line up again. So y equals x, t equals, I don't know what it is, something. Right, so the system recurs, right? So what's happening to your system is that it's basically, in terms of a wave, it's accumulating phase, right? So it's going from 0 degrees to 2 pi. 0 degrees is where it's here, 2 pi is where it's completely overlapped, and at phase of pi, they're completely, the original wave function and your next wave function at a different time are destructively interfering, or they're equal and opposite, right? So the wave will propagate relative to that fixed point. Right? So now, how do we measure, how do we plot that? Let's draw a circle. How do we plot the distance, or the phase difference between psi x t equals 0 and psi x t equals the recurrence. We'll call it 2 pi. Or t equals k. We'll change k. So here's a circle. We're going to draw it with radius 1. It's a really bad circle. So let me put the reticle or the grid right in the middle to compensate for my poor drawing. So here's my circle. I'm going to start at t equals 0, or phase equals 0, angle equals 0 here. Right? This is theta equals pi. Theta equals pi over 2, and so on and so forth, right? And so what happens to and now what I'm measuring is the phase difference between the t equals 0 signal, this red one, and the signal at some time, later time, right? And what happens to that phase angle, the difference between the two signals? Well, it precesses. It increases to pi over 2. That's where they're halfway out of phase. It progresses to pi eventually, where they're completely out of phase. And it comes back again, right? And it cycles through this circle over and over again. Okay, so the state of your system is specified by psi of x at t equals 0, right? That's the sine wave. And the phase angle difference between psi of x t equals 0 and the point you're looking at, called psi of x equals t prime. Right? So maybe t prime is right here. Well, whatever it is. Okay? What are the coordinates of that position? Well, remember the radius is 1. So the coordinates of that position are cosine theta, sine theta. Okay? And you have a function that progresses in a circle in time. So now the question is, so that means that psi of x comma t is going to be psi of x t equals 0, right? It's the original sine wave, times some phase factor that accounts for the fact that the phase is moving in time. And what function satisfies this property? Turns out it's e to the I theta. All right? So the way that you encode this phase change, the fact that the phase of your signal over time is changing and phasing in and out with your original signal, means that the time is propagating angularly, like it's rotating around a circle. And that's e to the I theta. Recall, maybe you learned this in Algebra 2 10 years ago, however long it was. So this signal right here, this point right here in time, can be represented by an angle and an imaginary symbol. All right, you need to have this I in here. All right, so to encode this fact that the system is progressing in phase from the original point to some new point, and in order to account for the fact that it goes over 2 pi, you have to have a factor of e to the I theta. Therefore, the system evolves on the complex plane. Right? If you remember the complex plane, here's the number a plus bi. The x-axis is at a and b is at b. This is the real axis and this is the imaginary axis. And to represent that as a circle, as a point on a circle, that's e to the I theta, where this is theta. Okay? This is where the complex comes in. Right? The fact that the system is a wave and it oscillates like a wave in time means that you have to include an imaginary phase factor, this I in there, which makes your wave function complex. Okay? So quantum mechanics, because the objects are waves, they are inherently complex valued functions because they oscillate. And the only way to encode an oscillation as a function of an angle is to include this imaginary phase factor. Okay? It's kind of strange, but the math works out beautifully, right? This was, a lot of people had a real problem with this, don't get me wrong. This was a real problem for a very long time. People were not happy about the idea that you're encoding real physics, real measurables, real things that you can measure in real life with an imaginary number. But the math proves that. Right? Everything it correlates exactly with this option, right? That because you're a wave, you have this imaginary propagation of your phase, and that leads to an imaginary wave function. Right? We can make choices about our wave functions to make them completely real, right? And we'll do that because this part right here is real, completely real. Right? So we can pull that out and just look at the real part and calculate psi squared. Right? So these numbers are inherently complex. Right? That was a little bit of a divergence, but that explains why there's an I in the momentum. Is that the momentum has this oscillatory property. Right? We'll be able to prove that once we get to in a couple weeks, and that's why you have an I in it. So let's go back to this now. 10 minutes earlier, we were talking about momentum, and we said that momentum is minus IH bar d by dx. Okay, so to get kinetic energy, we have to square it. So I'm going to write 1 over 2m times the mass of the electron, and now we need to calculate the square of this. So that's going to be minus IH bar d by dx, minus IH bar d by dx. Okay, so we get a factor of h, so the minus 1's cancel out. We get a factor of h squared. 2me. What happens when you multiply I by itself? What do you get? It's I squared. I'm sorry? Negative 1. There's a negative sign here. And the derivative of the derivative is the second derivative. Okay? So that's the kinetic energy. The kinetic energy of the operator for kinetic energy is h minus h bar squared over 2me times the second derivative of the wave function. Let's plug that in over here. Okay? now what we have is an equation. Remember that we now have, what that means is that the energy, when we apply it to the wave function, operator wave, we get a number back, that's the energy, times the wave function again. Right, we get the energy back when we apply this. Okay? So let me go ahead and take this real quick. We'll hold on to this. I'll write it here on the board. Okay, so now let's write that equation out. So here's our operator for the energy, total energy of our particle in a box. Minus h bar squared, 2me, times the second derivative of the wave function. Right, we're applying it to the wave function. And we get a number out times the wave function. Okay? Well, that's an equation, right? We can solve this, or at least we think we can. Let's rearrange it a little bit. Let me make sure I have my math right here. And you just do a little bit of algebra, and what you get is that the second derivative of this is all satisfied if you take the second derivative of some wave function, and what you get back is this 2me over h bar squared number times the wave function itself. In other words, we're taking the second derivative of a function with respect to its variable and getting a number out times that original function. Okay, so the wave function satisfies this important property, that when you take the second derivative of the function, you get the same function back. Can we think of functions that when you take derivatives, you get the same function back? That don't change. Something to think about for a second. Any ideas? What are some functions when you take the derivative of them, you get the same function back? Anyone remember? So obviously it's not x squared, right? It's not a polynomial, right? Because if psi were x squared, of course it doesn't integrate to 1, so that already fails. But d squared y dx squared is 2. Well, we don't get the function back, right? And we take the function, we should get back x squared times a number. But we don't, we just get 2, so it can't be that, right? So what are some functions that when you take the derivative of them, they come back the same? And here's a hint. What's the derivative of e to the x? No. E to the x. What's the second derivative of e to the x? E to the x. Okay, well we have there's a good guess. But what's the problem of e to the x? Well, if we take the wave function squared and then integrate from negative infinity to infinity, it's infinity. So that's no good. Right? It doesn't satisfy the normalization properties that we want. Right? This integral has to equal a number, it has to converge. So it can't be that. However, what if I take e to the ix? Well, that is cosine x plus I sine x. Now let's take the derivative of that. What's the derivative of cosine? Negative sine x. What's the derivative of sine? All right, let's take the second derivative of that now. Let's take another derivative. Derivative of negative sine x, negative cosine x, and the derivative of cosine x is negative sine x. Same function times minus 1. Right? Now we're getting somewhere. Right? Well, this should be like, okay, well that makes a lot of sense. We already said the electron should be a wave, so its function should look a lot like a wave. Cosines and sines. The problem is I don't want to use imaginary numbers here because they make things complicated. They're perfectly valid, right? I've explained to you exactly why they're valid. And there's good reasons to use complex numbers, but good luck trying to plot, right? We're going to calculate this wave function. We're going to want to plot it. Well, if it's imaginary, you're not going to be able to plot it. So what we should do instead is take a trick, is to do a trick. Is instead just take the real part of this. Right? And what we find is that psi will satisfy the following expression. Our solution. There's a general solution, I guess is probably a better way to write it, where psi of x is some, we haven't determined these numbers yet, some a times cosine of kx plus b of sine of kx, where k is equal to the square root of 2 times the mass of the electron e over h bar. All right, that's just this number, but square rooted. All right, you've seen this number already. That's where this comes through. Okay? So what I've done is I've just dropped the I. Okay, so I've taken out, so it's either going to be a cosine or a sine. I'm not sure which one it is, but we might be able to come up with do some algebraic tricks to determine the numbers that are a and b. So a and b left to be determined. We can use a little bit of algebra to determine them. And that's what our wave function looks like. Right? It's a wave. It's exactly what we expect. Right? We expect the electron to be a wave, and the function that represents its physics are a wave. And the frequency of the wave has something to do with the energy of the system, right? The frequency of the system. Right? The energy is encoded inside of the wavelength of the frequency of the cosine. That's exactly what we want. Remember the photoelectric effect, that the energy of a wave is proportional to its frequency, right? And the energy is inside of the cosine where the frequency is, right? And notice that the energy is here. So the wavelength or the frequency of the wave is proportional to energy. Well, that's what the photoelectric effect tells us. And notice that it's not a part of the amplitude. That's what classical physics tells us. Classical physics says the brighter the wave, the more energy it pumps into the system, right? That's what Lord Rayleigh thought. But in fact, the physics tell us that the energy is encoded inside the wave. It tells us it's about the frequency of the wave. So it's the frequency that determines the energy, right? All in here we've already proven all of these things that took a million years for physicists to figure out, and we just assumed a couple of things. That's saying a lot. I've made a large logical step here from that it took some of the greatest scientists in the world to figure out, but we get out of it exactly what we expect. We expect this to look like a wave. Everything is screaming for us that we should get a wave for our wave function, including the name wave function, and lo and behold, we know that the function that specifies the behavior of our electron in the box is a sum of cosines and sines. It's a wave. Right? Nothing exciting here. Nothing dramatic. The drama is that it's a wave, but the math is no surprise. So let's see. We've got 4:30. We got 10 minutes left. Yeah. So before we have just enough time. Let's figure out A and B. Okay. And then we'll stop from there. Okay. And we'll come back to what we'll want to do. At the end of this class, we'll have the wave function, right? We'll know exactly what this wave function looks like. We know the functional form. We can start asking it questions, right? And that's what we'll do next class. So let's just determine A and B. So we know that our system is specified by this function. And what we can do is think about the box to determine what A and B are. Okay, so we need some conditions. So some boundary conditions. If we think about if the electron is outside of the box, it's not there, right? So the wave function should be 0 here and here. Right? The wave can't exist in those regions, so there should be no wave function. There should be 0. So the wave function only exists in the region of the box. So now the question is, what's psi of 0 and psi of L? Well, those walls are infinitely high. So psi of 0 must be 0 as well, and psi of L must be 0 as well. Right? You can say that the wave function ends at those limits. Right? So you know that the wave function should kind of look like this. So psi of 0 is 0, and psi of L is 0. Not only that, the wave function must be continuous and smooth. So it can't have any divots in it or places where it doesn't exist. So the limit as x goes to 0 from the right of psi goes to 0. And the limit as x goes to L from the left of psi must also be 0. So what does that mean? What does that mean? Let me redraw this. So I'm just going to draw the box about the limits. And with another color, draw the wave function. What that means is that the wave function as it approaches the limit has to come in smoothly. Right? It can't just go like, it can't just do this, right? That doesn't have a derivative there. It's not smooth. So that's no good. So what you want is a function that arrives smoothly to the boundaries, continuously and smoothly. Okay, so it can't just be a sharp cutoff. It has to smoothly go out. Okay, so that limits the kind of things that you can put for A and B here. Okay, but we can figure out some things really easily. So if psi of 0 is 0, then A cosine 0 plus B cosine sine 0 is 0. Right? What's the cosine of 0? Anyone remember? Does anyone remember what the sine of 0 is? Remember, that's the y-coordinate at of a circle at 0 degrees. 0. What's cosine then? 1, right. So this is A equals 0. Okay, easy enough. Right, this goes away, and you're left with A times 1 equals 0, so A has to be 0. And if psi of L equals 0, then A cosine L KL plus B, this has to go away, so there's no cosine, right? A is 0, so B sine KL is equal to 0. So there's two choices here. Either B is equal to 0. Well, that's meaningless because then the whole thing is 0. So this is trivial. Right? B is 0 and A is 0. The wave function is 0. So, and the other one is where K times L is equal to some integer number of pi. Okay? So only other places where this is 0 is where the sign is 0, right? So that's either going to be at 0 pi, which is 0, pi, 2 pi, 3 pi, 4 pi, 5, 6 pi, and so on. That's where sine is 0. So that means then that K, this is only satisfied when K is equal to n pi over L, where n's an integer. Just to remind you, 0, 1, 2, 3, and so on. But we also define K to be the square root of 2me divided by h bar. Well, geez, look, energy, right? We already have a formula for energy now. 2me over h bar equals n pi over L. What does that mean? Well, what that means is, once you do all the math, the energy, we already know the energy of our system. The energy is going to be h squared, n squared, over 8 me L squared. Right? I'm just doing your algebra here and canceling out some of the pi's. That's why h bar goes away. right? You have to take a square. You have to take a square here to get E out, right? So that's where all these come from. But once you do this evaluation, you get this number. Look at how interesting this is, right? So the energy of our electron is determined again by h, which we expect. It's determined by the length of the box and its mass, but it's also determined by a number. Right? Energy is quantized. Right? This electron can only exist at specific energies. It can exist at energy equals 0, where n is 0. It can exist where E is equal to h squared over 8 MEL squared. That's where n equals 1. It can equal 4 times that, right, where n is 2. 9 times that, n equals 3, but nothing in between. Right? So by just assuming that the system is a wave and solving it like a wave, we automatically come up with the result that Planck and Bohr and all the other guys proposed. Just naturally, it comes out. The only way to satisfy a non-trivial wave function is when the energy is quantized. Right? We've already built this quantization. It comes out naturally from the math. How much time do we got left? 5 minutes? Great. 5, 10 minutes.
Cypher, I think that clock's behind.
Is that clock behind? Am I out of time? Okay, all right, that's fine. We kind of stopped where I wanted to be anyway. We'll come back to this. All right, so we still haven't determined B yet, but we will. We have one more trick to do. But that's not important. What's important is that we've already calculated the energy of our system without even looking at it. Right? It just comes out naturally from our analysis. And it's quantized exactly the way we want it to. All right, so we'll analyze this a little more in detail on Wednesday. Talk about what the wave functions look like. We'll finish this solution. And start asking it real questions. All right, start doing math. All right, have a lovely day, guys. Homework will be posted tomorrow, and it'll be due in a couple weeks.
Have a good night.
You too, thank you.
See you after supper.
Take care.